Então, o negócio é o seguinte. Vamos começar pelo problema. O problema de Big Data. A propósito, outra coisa. Vou ter que fazer um disclaimer aqui. Eu falo português, mas como vocês já estão vendo, meu português é horrível, porque quando eu mudei do Brasil eu tinha 17 anos. Então, o meu português é um português de uma criança de 17 anos. Então, vocês têm que me dar, tem que ser legal comigo, não judia do meu português, ok? E vai ter umas palavras em inglês jogadas aí. Então, é o seguinte, ó, o problema do Big Data. Primeiro, o universo começou a existir, depois os dinossauros desapareceram, e depois a gente começou a guardar muitos dados. O custo de guardar dados, o custo de storage, começou a cair muito, muito rápido. Lá na metade dos anos 2000, o custo da gente guardar dados, de guardar informação, despencou. E com isso a gente começou a guardar tudo. Então, até informação, até dados que a gente olhava e falava, não sei se um dia eu vou precisar usar isso, a gente falava, pô, mas guardar isso é tão barato que não tem por que não guardar. A gente começou a guardar tudo. Agora, o problema disso é o seguinte, que quando a gente começa a guardar muito, a gente começa a querer entender o que está dentro desses dados. Então, todos esses logs, todos esses files que a gente não prestava atenção neles, agora a gente começou a guardar e começou a tentar processar. Quanto mais volume que você processa, o processamento dele fica mais devagar. Quanto mais a gente tenta fazer, mais devagar fica, né? Então, o que a gente fez naquela época era começar a jogar mais hardware em cima. Quanto mais dados, a gente pôs mais hardware. Quanto mais dados, mais hardware. Só que o problema de jogar mais hardware no problema é que a física não deixa a gente ir muito longe com isso. Toda aquela física de emissão de calor nos processadores dos computadores tem um limite. Então, chegou uma hora que a gente não pôde mais pôr mais músculo no hardware e os dados continuaram a crescer, o volume de dados e tudo começou a ficar mais devagar. Aí chega uma hora que não tem mais como você fala, pô, eu quero continuar processando tudo isso, mas é muito devagar, não tem mais o que fazer. Bom, para a gente explicar o que é Spark e por que eu estou falando tudo isso, a gente tem que falar um pouquinho de M&Ms. Não me pergunto por quê, mas o meu M&M favorito é o cor de laranja. Eu sei que todos eles têm o mesmo gosto, mas eu gosto do cor de laranja. Não entendo, mas eu gosto. Então, se você me dá uma jarra de M&Ms, e você me falar, tá, você gosta de cor de laranja? Vai lá e conta quantos M&Ms cor de laranja tem. Numa jarra assim, ia ser um trabalho chato e tedioso, mas dá para eu fazer, né? Até dava. Mas e se isso aqui acontecer? E se você me der 100 jarras de M&Ms? Eu podia sentar lá e gastar 100 vezes o mesmo tempo e contar todos. Podia. Mas, rapaz, quando chegasse na jarra 17, 18, eu ia jogar a jarra na parede e ia desistir e ir embora, né? Agora, eu posso ser esperto e falar, bom, mas tem quantos de vocês aqui? Uns 200? Se eu tenho 100 jarras, eu falo, ó, os primeiros 100 aqui, vocês vêm aqui, eu dou uma jarra para cada um, e eu fico aqui. Quando você acabar de contar, você me diz o seu número, eu fico aqui com um papel e uma caneta, eu escrevo, somo todos os 100 de vocês, o número que vocês me dão, e no final eu tenho o resultado. Isso é mais rápido ou mais devagar de eu contar sozinho? Muito mais rápido. Quanto mais rápido? Teoricamente, seria 100 vezes mais rápido do que eu fazer sozinho, né? Porque eu não preciso fazer em série, eu posso fazer isso em paralelo. Essa ideia de processar dados em paralelo é o que fez a gente poder processar esse volume de dados que a gente está crescendo a cada ano, a cada dia, de uma forma, numa velocidade que é aceitável, né? Esse processo começou com Hadoop. O Hadoop mostrou para a gente, anos atrás, que essa ideia de paralelizar o processamento de dados tem muito potencial. Só que tinha uns problemas com o Hadoop. Ainda tem, né? Bom, se você me perguntar, eu acho que o Hadoop está morto já. Mas o pessoal ainda usa, né? Os dois problemas grandes do Hadoop, na minha opinião, é o seguinte. Uma é que, se a gente voltar para a nossa analogia do M&Ms, se eu te desse 100 jarras de M&Ms e falasse para você, ó, cada um conta uma e eu tenho que contar todas, o que o Hadoop faria é o seguinte, ele deixava o papel e a caneta aqui, aí quando você falasse, eu acabei de contar, o Hadoop vai até lá, pergunta para você o seu número 20, aí corre aqui de volta, escreve 20. Aí o outro ali fala, ó, eu acabei também, aí o Hadoop corre lá, pega 17, o Hadoop faz essas viagens 100 vezes, até vir aqui e somar todos os resultados. O Hadoop, cada vez que precisa fazer um load de mais dados, é outra viagem até onde esses dados residem. Dá para fazer, mas logo você perde muito tempo. E a outra coisa do Hadoop é que faz tudo no disco, o que é mais devagar. Quando os caras que começaram a escrever as primeiras linhas de código de Spark pensaram em fazer um produto novo, uma máquina nova, um motor novo para processar esses dados, esses foram os dois problemas que eles identificaram no começo. E o Spark resolve esses problemas de duas formas. Uma é que o Spark, dessas 100 tarefas que o Spark tem que fazer, o Spark faz de uma viagem só. Ele tem vários níveis de tarefas que não precisa fazer 100 viagens até onde os dados residem para calcular eles. Uma viagem só traz todos os dados de uma vez, aí depois processa tudo de uma vez e adiciona, agrega tudo no fim de uma vez só. E a outra coisa que o Spark é diferente do Hadoop é que o Spark faz tudo em memória, o que não diria que seja mais barato, não é o jeito certo, mas é com certeza muito mais rápido, né? E a analogia dos M&Ms funciona se você olhar na estrutura de como o Spark, na estrutura de um cluster de Spark. O cluster é um conjunto de máquinas, um conjunto de VMs, digamos, trabalhando juntos nesse processo paralelo. Então, numa estrutura de Spark, tem uma máquina que a gente chama de driver. Nesse caso, no exemplo de M&Ms, eu seria o driver, a pessoa que está agregando tudo e recolhendo todos os resultados. E tem as outras máquinas que são os executores, que são vocês contando os M&Ms para mim. O driver decide qual executor vai fazer o quê. O driver divide os dados em grupos que a gente chama de partitions. No nosso caso, cada partition é uma jarra de M&M. E manda uma partition para cada executor. Aí fala, executor 1, você vai contar esse, executor 2, você conta esse, executor 3, você conta esse. No final, os executores acabam de fazer as tarefas deles, mandam os resultados de volta para o driver, e o driver apresenta os resultados para os usuários. Você pode ter um cluster com 4 executores, com 100, com 1000. Tudo depende do volume de dados que você quer processar, quantos partitions você tem, mas se você souber escrever o seu código de um jeito inteligente que utiliza esses executores da melhor forma possível, a velocidade que você pode ter em Spark para processar Big Data é muito grande. Ok? Eu tinha 10 minutos, eu já passei desses 10 minutos. No final, se vocês tiverem pergunta, como o Luiz falou, usa o Slido. No final, se a sua pergunta não for atendida, a gente vai estar por aqui. Tem mais uns colegas meus da Databricks aqui. Eles falam português pior que eu, acredite ou não. Então, mas se você tiver alguma pergunta, no final, acha a gente aqui e a gente conversa mais sobre isso, tá bom? Muito obrigado. Jorge, your turn. Obrigado.
Hi, everyone. Let's see, let me change it over. Okay, well, thanks everyone for coming out. We're really happy to be here to share with you guys, a little bit about Databricks and the way we see machine learning working on our platform, right? So to start off with, let me just tell you a little bit about me, so you have some context, right, of who I am. So in Databricks, I'm a solutions architect, and I typically work with clients and prospects, right, to try to find out what they're trying to do around data management and machine learning use cases. And typically, I work with them to come up with solutions using our product. So that's my background. Before I joined Databricks, I was with another company called Hortonworks. They have a big data distribution, so I've been in the space for a long time. And then before that, I was a software engineer for a long time as well. So that's my background, right? I'm curious to see, we have a lot of people here. But, could you guys show, raise your hand, I guess, if you come from a software development background? Okay, good. So that's about, 25% of you guys. What about data engineers? Okay. And data science people? Okay, so it's a good even distribution of people across the board. Okay, good. Thanks for that. So to begin with, I guess, let me these are some of the things that we're going to cover today, right? So I'm going to be talking for about 30 minutes or so, and I'm going to be switching back and forth between slides and demos. So some of the high-level items that we want to cover today is, who is Databricks? So some of you may already know who we are. Obviously, Andy just went through, a little bit about Spark and what that is, and the motivation for Spark. So I'll cover a little bit about Databricks. I'll also cover a little bit about how data science use cases are typically implemented with Databricks, including deep learning as well. And then at the end, I'm going to cover a little bit about MLflow, which is one of our products as well that comes with the platform. So to begin with, sorry, I guess this keeps going up and down. So Databricks, right? Who are we? So for those of you who know about Spark, Databricks is a company that was founded by the people who created Spark about 10 years ago, right? So the company has been around for, 8 years or something. And the same people that created Spark created Databricks, and basically our mission in life is to provide a unified platform to enable people to do data engineering and data science use cases, right? That's what we try to do. We have a lot of customers all over the world. About 2,000 customers use our products on a daily basis to do anything around, like I said, machine learning and data science use cases. I guess before we get into it, one of the things that may be beneficial, especially to you guys who come from a software development background or data engineers, you may not know, you may not be very familiar with what data science is, right? So let's talk about that a little bit. So in data science, typically, there's a lot of other things that happen before you get to actual machine learning development. For example, a big part of your day-to-day and the time that you spend during the day is around data, working with the data, right? So typically, you have to collect the data wherever it may be, right? It can come from a database, from text files, CSV files, things like that. You may be getting the data on a regular basis from like a messaging system like Kafka. So typically that, a big portion of your time is spent dealing with the data, right? Aggregating the data and getting it to a point that you can work with it. Along with that, there's a lot of data validation, work that has to happen. Typically, people have to clean the data, filter it, do things like that. Then there's a big amount of work that goes into creating features. So typically, anytime you do any sort of machine learning use case, you typically start with the data, and you're trying to find meaning in the data so that you can do a prediction with a similar data set later in the future. So that's all part of the feature engineering box here. Once you do that, you typically do your machine learning development, right? So that's when you use the models or any frameworks that you may be using, like scikit-learn, for example. At the end of that, you end up with a model, which is essentially a function that takes as input a whole bunch of data sets and then gives you a prediction, right? Once you have the model developed, you typically have to deploy that so that you can use it in production. And there's different ways that people use it in production. But there's a lot of work that goes around managing the models, the model lifecycle in production, from deploying it to versioning it, to monitoring it and improving it and things like that. So there's a lot of stuff that happens in the machine learning lifecycle. And what we strive to do at Databricks is to essentially help with everything from start to finish to enable people to do more with less time. Like I said, Databricks essentially brings together both worlds of big data processing. Andy talked a little bit about Spark and what we do there. And essentially, we enable you to get data no matter where it comes from. Typically, you run a set of pipelines that modify the data in different ways, and then you store it in a different, in a destination. Once you have the data in a state that can be used, we also have tools that allow machine learning data scientists to work with the data and then come up with the models, right? So from a very high level, that's our platform, and that's what we do. We're a managed platform that sits on top of AWS and Azure. So whichever cloud you're using, we can essentially you can use Databricks in it. From a very high level, these are the three pieces that make the platform. The runtime is basically where everything happens. That's where you have the Apache Spark runtime that allows you to manage and modify the data as you wish. We also have additional features there like Databricks Delta, which we'll talk a little bit about, and as well as machine learning frameworks that are built into the platform, like Scikit-learn, TensorFlow, and others. And then at the top of it, we have what we call a workspace that allows you to interact with the system, basically, through a UI. So Databricks, the workspace and the way that people use the tool is basically through a UI. And essentially, there's three main concepts within the workspace that people typically deal with. One is the clusters. So I think Andy was talking about the clusters and the VMs and how the executors are managed. And that's essentially what we do with the platform. We allow you to auto-scale the clusters, to launch them, to kill them, and things like that. And then we also provide a set of notebooks that allow you to essentially write pipelines. If you're doing data engineering work or machine learning, you can essentially use these notebooks to do your work. And then the notebooks themselves, they have a lot of features. For example, Git integration, permissionings, and things like that, that a lot of people typically find valuable. And then at the end, of course, you typically want to schedule these notebooks to run on a regular basis. And we also have a built-in job scheduling feature as well within the platform to allow you to do that. So I'm curious, before I go into the demo, we'll go into the demo and we'll talk a little bit about Databricks and we'll go through a few things. Who here has ever used Databricks before? Okay, so I don't know, about 20% of you guys. Okay, so for the rest, hopefully this will give you an idea of how Databricks works essentially. So let me jump over to that. And by the way, during the next 30 minutes, what I'm going to be doing is I'm going to be jumping back and forth between the slides and demos. So I'll do this a couple of times to break up the actual demo into different pieces. But essentially, this is Databricks. And when you jump into the UI, essentially, you log in and you have access to a number of things, right? Like I said a little bit ago, most people spend most of their time in the workspace area, but we also have the cluster area. So let's go there first. And the reason why I like to start here is because everything you do in Databricks, whatever you run, has to execute within the context of a cluster. Before Databricks, and especially like with some of the on-premise Hadoop distributions like Cloudera and Hortonworks, and I know this firsthand because that's where I come from. Managing a cluster is actually very expensive and very complicated. There's a ton of companies that have clusters that are pretty sizable. They actually spend a lot of time just managing the cluster. So they don't do any value-added use cases. All they do is manage the cluster, and it takes a lot of work. And with Databricks, we actually made this process very, very simple. So when you create a cluster, it's a matter of like clicking a few, filling out a form, right, to specify the size of the cluster. And typically, the size of the cluster depends on what you're doing. So if you're doing a development use case, you may be able to do this with like a very small cluster of like 3 nodes. But eventually, when you deploy jobs to production especially, if you have a lot of data, you may want to deploy a cluster with like 20, 40 nodes and so on and so forth. So it's the same thing. You use the same form. This basically allows you to control everything, right? So you specify the name. Some of the important choices that people make here are the runtime version. We have different versions of the runtime that have different versions of the underlying components that are part of the runtime, right? And all of this is documented, so you can always look up, what components make up every single different runtime version. But some of the, this is where you define essentially the size of the cluster. So like I said, when you start off developing with the platform, most people just use a couple of nodes in the cluster, and that's usually good enough. We also have auto-scaling. So essentially, this allows you to run jobs on the cluster, and the cluster essentially goes up and down, as needed. So this is pretty easy. Once you define the name of the cluster and the options, you can essentially just start the cluster. And once you start the cluster, you end up with something like this, right? So let me go back to this. So this is a very quick demo of what you can actually do in the workspace, right? Typically, and what I'll do is I'm going to jump over here. Typically, what you do as a data scientist or data engineer, you usually start with data that comes from a given source, right? So out of the box, Spark and Databricks, we support data coming from any number of data sources. Like if you have data in any blob storage, like S3 or ADLS, for example, you can read that data. If it comes from a database or a messaging queue system and so on and so forth, all of those things are basically integrated out of the box where you can simply use them. The file formats that we support are the common ones, right? So typically, especially if you do machine learning use cases, most of your data sets come from things like CSV files, for example. Typically, people have a lot of data like that. In addition to other formats like Parquet and JSON are two common ones as well. For those of you who are data scientists, obviously you probably are familiar with pandas and the idea of data frames, right? So in Databricks and Spark as well, anytime you read data, no matter where it comes from, you end up with a data frame, right? So the first thing you do as a user is you point the data frame, you create a data frame to read data. In this case, we're reading data from a JDBC source, so we're basically reading a table. In the end, you end up with a customer's data frame that has basically columns and rows. You can also read data like JSON data, for example. This is coming from a file system. And then, of course, one of the biggest benefits of using Spark is the idea that you can distribute the work, right? So if you're dealing with a lot of data, you can essentially distribute the work like Andy was describing a little bit ago, where the data sets can be read in multiple nodes. When you join this data, when you sort it, when you group it by, or when you do any sort of analytics on it, you essentially distribute the work, right, on the nodes. And from a data frame API perspective, is really simple. You can essentially do a lot of the SQL-like operations on these data frames. Like in this case, we're taking the two JDBC data frames and the JSON data frame, and we're joining them. So you can essentially do joins, you can do filterings, you can do any number of things. At the end, you always end up with the data frame, which is essentially, again, just a table of data. Typically, once you finish the processing, you end up with the data frame that has the data in the state that you need. And then at the end, you typically send that data somewhere else. So in Spark, it's really simple. You simply say write, and then you tell it where you want to write the data to. Like in this case, we're writing it to Delta, which is a format that we'll talk about in a little bit. But it's basically a format on top of Parquet. You give it the location, and then that's it, right? Then Spark takes care of the rest. And essentially, you end up with files that represent that data in Parquet format. One of the biggest benefits of using like a notebook type of development environment is that we support Python, R, Scala, and SQL. And this is very beneficial, right? Because as an end user, especially if you have a team of people that are working on one project and you have some data analysts who are very familiar with SQL, they can use SQL on these data frames that you construct. They can simply use SQL. But if you have a data engineer who prefers using Scala, for example, they can do that as well. And typically, machine learning people or data scientists, they like to do stuff in Python because there's a lot of frameworks to support those use cases. And of course, they can do that. In Databricks, you can essentially switch. So once you have a data frame, you can create a temporary view and then very easily switch between the languages. So for example, before we were doing stuff in Python, and then here we can simply switch over to SQL and then write SQL. So when I work with customers and they're new to Databricks, right, and Spark in general, this is pretty powerful because even if you're a person who likes Python, a lot of times you can actually think of a problem in SQL a lot easier, and this allows you to do that. So this is something that you don't typically have in other frameworks where you can just switch back and forth, basically. Another thing that we have is these visualizations. So once you have the data frames defined, like in this case, we have the reviews data frame, you can essentially do any SQL, like I said. And then in addition to viewing the data in a tabular format, you can also basically do visualizations. We support many visualizations out of the box. And that's typically very beneficial because when you're doing a data science use case, the very first thing, well, one of the first things you do, like I mentioned earlier, is you try to understand the data. And the way people try to understand the data is by visualizing data in different ways, right? Whether you're trying to find the distribution of the data that you have, or you're trying to find averages and things like that. This idea of visualizing the data within the notebook is pretty powerful. If in addition to the built-in visualizations, of course, some people prefer other visualizations libraries, and you can bring those over as well. This is one little example where I'm using an R library to take the same data that we're working here with, the reviews data set, and essentially doing a word cloud visualization, right? So it's pretty powerful. I'll skip the machine learning for a little later, but we'll talk about that in a little bit. So hopefully this gives you some idea of, what Databricks is, how you work with the data, right from the source, wherever it is, how you manipulate it in different ways, and then how you work with it at the end. So let me switch back to the presentation. And let's see, where am I? So I'll talk about Delta. Let's see if this works. Okay, it works. So one of the features that is part of Databricks is something we call Databricks Delta. It's a project that was actually open sourced a few months back. And this is a feature that essentially gives you a lot of benefits when you're dealing with data, especially, well, on the data engineering side and the data science side. Essentially, when you have a set of pipelines, like if you're an organization and you have 100 different jobs that you run every day to move data from point A to point B in different ways, without Databricks Delta, what a lot of people end up having to deal with is a lot of reliability problems. And those include if a job in production fails, you typically have to figure out how to recover from it. And of course, you can do it. People have been doing it. Databricks Delta basically solves that for free for you. And the way that it does it is by using ACID support, basically, so that if you're modifying a Delta table and you're inserting data, either the whole data set completes or nothing is changed, essentially. The quality enforcement is another problem. So as you work with the data, over time, the data schema might change. And without Delta, essentially, you as an end user have to figure out how to manage all that schema evolution. Databricks Delta basically, again, solves that problem. Another big problem that people typically have is when you get to a point where you have a lot of jobs. For example, you may have some jobs that are constantly receiving data from different, in different ways. Like if you're constantly getting transactions that you need to process, and at the same time, you have batch jobs that you want to run hourly or nightly or whichever other schedule you need. There's typically, collisions in the way the data is, manipulated. And again, with Delta, it solves that. And the way that it does it, it's there's a lot of reasons why it solves all these things, but these are some of the high-level ones. So, like I said, ACID transactions are part of Delta, which essentially say whenever you have a pipeline that runs, when you write data to a table, either everything works or nothing works. Just the semantics are very similar, right, to what you have in a relational database system, except this is done at scale in a distributed fashion. Schema enforcement is another one that I talked about. So basically, if you try to write data to a table and it does not conform to the schema, it will fail, right? You have to basically tell it that you meant to do that explicitly. And then the idea of unifying different jobs that write to the same table, at the same time, basically concurrently, that is also supported. So Delta is really, really good for that reason, right? So people typically architect their data lakes in such a way that all the data that is coming in from different data sources lands on what we usually call the bronze layer. So this is basically all the raw data, right? So this is more, I would say, on the data engineering side, because they're the ones who deal with this sort of stuff typically. But the data typically lands in a set of tables. Then from there, there's a set of pipelines that are run against that data. And the data is either cleaned or filtered, augmented, and things like that. You end up with a silver layer of data. And for the data scientists, they usually like to work at that level because the data is somewhat sanitized already. After that, there's also like a gold layer set of data, and that's typically done. It's typically aggregated business level data sets that is consumed by BI tools. So from a high level, this is how the Delta Lake looks. So having said all that, data scientists, like I said, they usually like to start with data that has already been processed, right? Sometimes that's possible, sometimes that isn't. It all depends on the company. But for the purposes of the discussion, I guess, let's say the data is already there, right? So some of the common tools. Well, this slides, I guess. Let me preface it. I guess this slide talks about if you come from a world where you're already doing data science, right? And about 30% of you guys are data scientists, I think. Typically, one of the first things that you have to do when you move into a distributed world, you need to compare and contrast what you already know to what's possible, right, in a distributed fashion. So this gives you a good idea of the tooling that's involved. So typical tools include Jupyter. And the equivalent for us is the notebooks, right, that we just saw. Pandas data frame, we talked about that a little bit. So for us, it's Spark data frames. All the other libraries that are listed here, we also support those. And we support those either if you're doing single node training or distributed training as well. So the point of this slide is that if you come from a data science background and you've been doing things in a certain way, there's usually a mapping that can be done basically to do it in a distributed fashion. In terms of some of the differences, right, between Databricks and Jupyter. On Databricks, we already talked about the language support, right? The built-in visualizations, and then the fact that it's already integrated with Spark, and how easy it is basically to switch languages. Some of those features, overlap with Jupyter, but I would say that a hosted notebook has a lot of benefits that Jupyter simply doesn't have. Like the idea of collaboration, right, between team members is very much doable in Databricks. With Spark and Pandas, when you make a switch, right, or you have a need to go from single node model training to distributed, there's a little bit of a learning curve that you have to do, but for the most part, the switch is pretty seamless, and we typically see people, getting used to Spark data frames quite easily. Now, as you know, or if you don't, Apache Spark, of course, is open source, right? And that's what a big part of our platform is based on. So some people, especially when they're new to Databricks, they want to know, well, why would I use Databricks, right? So there's several different reasons, right? Besides all the collaboration tooling that you get with us, just the Spark runtime itself it's also very much optimized on Databricks, right? So if you run a job on Apache Spark and you run it on Databricks Spark, you typically see a much better improvement in Databricks, right? And we've seen this over and over and over across many, many customers. And the reasons are, we have very well optimized connectors to data sources. We have optimizations within the framework. For example, we do a lot of caching in different places that you don't get with the open source Apache Spark distribution. And then in particular for data scientists, we have Databricks Runtime for ML, which includes a lot of the frameworks that typical data scientist people want to use, right? Like scikit-learn, TensorFlow, and others. And then Databricks Delta as well is there. So machine learning, right? You guys are familiar with it because, well, some of you are anyway. But from a very high level, especially me, when I first learned what machine learning was, I'm like, well, what's the big deal? What is machine learning? I come from a software development background. But essentially, from a very high level, you're essentially trying to learn patterns in the data without explicitly being programmed, basically, right? So this is why you use models. You essentially feed a lot of data into the models, and the models themselves try to learn why, the patterns basically in the data. At the end of it, you end up with a function, right? And the function basically takes the data points that you train the model with, and it gives you a prediction. So that's basically what machine learning is from a very, very, very high level. Another question that I typically get when I work with people that are new to distributed machine learning is, why would I use, distributed machine learning? I've been doing this on my laptop and it works. And there's typically two reasons why people do it, right? One is the size of what you're working with. Either the model or the data basically can get too big, where it no longer fits on your VM, right? So if you're dealing with, if you need to train your model on, 100 gigabytes of data, it may very well, not be enough. Your machine may not be enough for that. So that's one reason to use distributed machine learning, because then essentially you can break that work up into the different nodes on the cluster. And of course, you can size the cluster accordingly. The other one is speed, right? So even you might get to a point where you can train a model on a single laptop, but you may have to wait 24 hours, 48 hours for the model to finish, right? And again, this is all depending on what you're doing with the modeling that you're doing, but that's another reason. When you get to that point, you can again distribute that work. And I've seen customers that go from training a model that takes 3 days down to like hours or minutes sometimes, right? Depending on what they're doing. But those are the two reasons why they do it, right? Spark, scikit-learn is a very popular model. A lot of people start with that one because it's very, I would say straightforward to learn. When you get to a point that you need to distribute that, we have a library called Spark sklearn that essentially allows you to distribute the training of the model across the different nodes, right? We also have something that we call Spark ML. Spark ML is one of the main components, I would say, of Spark. Spark ML got a lot of inspiration, I would say, from scikit-learn, right? So you'll find a lot of similarities in the models that they have, and then the way you work with it, basically. But that's the newer library in Spark. So people typically don't use MLlib anymore. That used to be the old library, the old component. That was based on top of RDDs for those of you who know Spark, and that's why we basically don't recommend people do that one anymore. Spark ML concepts, and I think this is very similar to scikit-learn as well. You essentially have two types of classes that you work with. One is a transformer, and a transformer basically is a class that takes a data frame. So you have a whole bunch of columns, a whole bunch of rows with data, and then you essentially call transform on it, and it gives you a new data frame with with modified columns, right? And an estimator is the other main component that essentially, again, you start with with a data frame, you call a method called fit, and this is what essentially learns parameters for a model. So it looks at all the data, it does all the math and all the other stuff that's built into the model, and then at the end you end up with a function. So those are the two main concepts of Spark ML, and that's pretty much true for all the other machine learning frameworks. One very critical idea, I guess, in machine learning is the idea of a pipeline. So a pipeline essentially combines a whole bunch of transformers and estimators into a pipeline so that you can then just call the execution on this once, basically, and the pipeline manages calling all of them together. Let's see. So I'm going to switch over and do a Spark ML demo. Okay, the Wi-Fi is a little slow, but in this demo, what I'm going to do is basically I'm gonna walk through a Spark ML pipeline. Wow, this is really slow. Okay, so essentially this sample notebook essentially takes data that comes from reviews. So these are reviews on products that people left on Amazon. And along with the review, there's a rating that says, if the product was good or not. So basically here, we simply are reading a set of files that are Parquet-based files, and we, again, come up with the data frame. We create a view called reviews so that we can manipulate it in SQL, for example. And we simply display that, right, to get an idea of what the data looks like. So first, we want to get an idea of what the distribution of the values are. So we basically use SQL to do that. And we see that the majority of the reviews are 2s, 3s, and 4s, essentially. Once you have a data frame, we split the data between the training data frame and a test data frame. So that's basically here we're using the random split function of the data frame to do that. After we do that, we essentially want to know, with no model training, what is a positive review, and we just simply say, okay, anything with a 4 or more is positive. So what is that? And this is good basically because the hope, of course, is that you end up with a model that is going to give you a better idea, a better prediction of what you can simply do, with a very quick analysis, essentially. This is where we start with the different, basically, transformers and estimators. So the first thing we do is we do a regular expression tokenizer that essentially takes the review and breaks it up into different words, right? That's the first step we do. So we use this class to accomplish that, and then we essentially display it. That's the other thing that I typically see when people do pipelines to do either machine learning or data engineering work. With the notebook concept, you can essentially walk through your code and in between simply do a display, right? That's built into the notebook. And then you can essentially keep checking your code as you go. The next thing this thing is doing is basically doing a stop words remover to remove any words that don't really have any meaning, basically, in the review. You can manipulate the stop words, for example, in different ways. Then this essentially gives you, this is another estimator, essentially, that gives you, it's a count vectorizer estimator. And then here, we come up with a label, right, that says, okay, the rating, if the rating is 4 or more, basically, it's going to be a good review. And then the model itself, this is it, is a decision tree classifier, which essentially will take all the data that we have previously processed with the transformers, essentially, and then it's going to try to learn the data, right? So at the end of that fit, we're going to end up with a model, right? The model itself is simply a class that has coefficients related to the features that you fed the model, right? So that's all it is. And you can essentially inspect that, in different ways. Actually, this is a tree, not a coefficient-based model, but same idea. And that's it. So after you do that, you can essentially load the model, and then essentially evaluate it, right? So you can give it another. I don't think it's here. Okay, you can essentially apply that model in different ways to new data. So if you have a new review, you can take this model, give it the review text, and it'll essentially tell you if this is a positive or negative review, right? So this is just one example, but this gives you an idea of how it goes. And in a little bit, I'm going to show another notebook that is going to show another machine learning development use case in relation to MLflow, which I'll talk about in a little bit here. Okay, so once you have the model, typically, you want to do something with it, right? So let's assume that you've already defined the model, you've already trained it in different ways, and you got to a point where you're pretty happy with it, right? Typically, a data scientist will go through many experiments, right? They'll play around with different hyperparameters depending on the model they're using. And in the end, you end up with a model that you want to deploy. And typically, there's 3 different ways that people use a model. The first one is if you want to deploy the model and you essentially want to be able to execute the model in a low latency situation. So for example, if you create a model that detects fraud, right? Fraudulent transactions, let's say on a credit card. When you deploy that model, you deploy it as a REST API component, for example. And when a new application comes in for a transaction, or when somebody swipes their card and tries to do a transaction, that model can essentially be exercised, right? And you want low latency because you need to get the answer right away. So that's typically one of the most common ways of doing it. There's 2 other ways. There's a streaming way. So essentially, if you are, if you create a model to detect network activity that could be, malicious, for example, you may have a lot of streams coming in through Kafka, for example, representing different types of activity on the network. And at that point, you may want to apply the model to those events. And if they, trigger a flag, you of course want to raise an alarm. So that's another way. And then the last way is if you have a model and you have a whole bunch of data that you want to score on a regular basis, like every day, every night, every hour, whatever. Typically, you might have a set of data set with like, 1 million rows or something like that, and you want to essentially apply the model to that. So all these 3 ways, these are the 3 most common ways that people use models. And of course, you can do any of those, on Databricks. Let's see. Okay, so now, I only have a few minutes. I'm gonna switch over and I'm gonna show a demo of well, hold on. Before I do that, let me go here. I only have a few more minutes, so I'm just gonna jump into this because I think this is pretty important, and it's something that a lot of people are receiving really well. But in general, whenever you do any sort of machine learning, whether you have a team of 1 person or 10 people, typically there's a lot of moving parts, right? And the whole development lifecycle is pretty complex. Hold on. Yeah. So typically, like I said, you need to train the models. You need to keep track of things, of how different hyperparameters, for example, how different models perform on the data. You have to keep track of error rates and things like that. You have to keep track of versionings. You have to be able to deploy the models and update them as time goes by. There's a lot of moving pieces, right? And this is essentially what I just talked about, from preparing the data to training the models to deployment. And it's like a whole circle, right? It's a cycle. It repeats over and over and over. Every step typically uses different tools, for the task at hand, right? And there's a lot of tuning. There's scaling that you have to do. Like I said, a lot of people start with like a single node model development setup. But at some point, you may need to scale up or scale out. And so that's another problem that people face. Governance is another area that a lot of people are putting focus on. Because like I said, you want to know, for example, what data did you use to train Model X or Model 1 or Model 2 and so on and so forth. You need to be able to version them. You need to be able to roll back and things like that. There's the idea of exchanging models, right? Because as a data scientist, you may be responsible for training the models, for tuning the models. But typically, there may be somebody else in the org, like a DevOps person, who takes the model and deploys it to production, right? So there's typically different people who do different things. So this is where MLflow comes into the picture. So MLflow is another open source project. Anybody can go out and get it, right? It's out on GitHub. It gives you three main pieces to do different things. So the first one is tracking. And tracking from a very high level, if I'm a data scientist, and I want to try 3 different types of models, like linear regression and, I don't know, decision tree and XGBoost or something like that. I need to be able to test all of them and keep track of how accurate those models are. So MLflow tracking allows me to do that. It allows me to know exactly what code I used for every model that I developed. MLflow projects is basically a packaging format that describes a project with all the dependencies, essentially. And what that allows me to do as a data scientist is to take my project, hand it off to somebody else, and they can reproduce it on their end. And then the last one is MLflow models, which again is a general model format. And the reason why this is important is because it allows me to essentially serialize models from different frameworks in a common format and simply hand that over to like a DevOps person, and they in turn can deploy it to any number of deployment solutions, as you'll see. So on the tracking, this is exactly what I just said, right? Essentially, you have a tracking server that provides either a library or a REST API that, depending on what you're using to train the models, you can essentially send data to it. On the other end, once the data is captured, you have a UI and an API that you can use essentially to see that data. The projects is essentially a project spec, right? That allows you to capture the code, the config, the data that you have for the project, and then it allows you to execute that project either locally or remotely. And then the models, once you finish developing a model and training a model, you can essentially save it. They use a term called flavors. And the flavor basically refers to the framework that you're using to train the model, right? For example, scikit-learn, TensorFlow, and others. And then on the other end, basically you take that model and you deploy it. And you can deploy it either to a Docker container. You can deploy it to Spark itself to do batch or stream scoring, or a cloud serving tool like Azure ML or SageMaker. Okay, with that, I only have a few minutes, so I'm gonna jump back here, and I'm gonna give you, I'm gonna go through a demo for MLflow itself. So first, I'll do a quick start to show you how easy it is to essentially use MLflow. So from a very high level, the first thing people do is they wanna be able to track the models and the training and so on and so forth. So there's 3 main calls that you do to MLflow. The first one is when you want to log a parameter, right? I'll jump into another notebook in a little bit, but essentially you just do MLflow log parameter. Basically, it takes a parameter name and a value. You can also do metrics to log a metric as you're going through the training of the model. You can log the same metric different times, depending on where you are in the model development steps, to keep track of all those values. And then at the end, you also want to log either an artifact or the model itself. So from a high level, this is all it takes to use MLflow. MLflow is also included in Databricks, right? It's managed, and everybody that has access to Databricks essentially has access to it. Here, this notebook will show how to use MLflow within the context of training a model using scikit-learn. So I imagine some of you guys have used this diabetes data set, especially for those of you who are familiar with scikit-learn, but this is a test data set that they include. And from a high level, basically, we're reading the data set, right, from scikit-learn package. This one has one function here. So this is not specific to MLflow, right? This is just typical Python code, but this is just a function that takes some parameters and essentially creates an image for it, and it saves the image, right, on the file system. This is where the training code is. So this is obviously a very simplified version of a machine learning function. Typically, these functions are pretty big, right? But this gives you an idea. This function essentially takes in some data along with some parameters. And what it will do is it will take the data. It's going to be using logistic regression, I believe. And it's going to try to fit that data into the model. So basically, this is pretty common code where you essentially split the data that you have to work with to train and to test the model. Here, basically, it does some sanity checks on the parameters. Here, you basically tell it that you're starting a new MLflow run. So MLflow has this idea of experiments or runs where you can run any number of them. And this is the way you basically tell MLflow that you're starting a brand new one. This is the model that we're doing with the different data and different hyperparameter tuning, hyperparameters. Here, it's fitting the data. And like I said, it's pretty simple. But the idea is that here, we're basically computing the error rates of the model. And then at the end, of course, by line 51 here, we already have a model that's trained. We know what the parameters are, and we know what the error rates are. And so we essentially use MLflow to log all of that, right? So we log the parameters, we log the metrics, we log the model itself, and we also log the image that we created. So the idea as a data scientist, you typically run through this many times, right? So basically, that's what hyperparameter tuning is, where you keep changing the hyperparameters of the model. And of course, that's model dependent. Different models have different parameters that you can tune on. But you call that many times. In this case, I think I called it twice with different parameters. When you do that, you can go to runs. And these are the experiments that I've executed here. So it's integrated into the workbook. You can jump out, and you can see the MLflow specific details for this experiment, right? So when it comes out, these are all the experiments that you've run. For each of them, you can essentially see the parameters, the metrics, and so on and so forth. You can also see the model that you saved, as well as anything else that you might have attached. You can also save the data itself that you use for the model training. Obviously, if you're training with a big data set, you should not be saving the data here, but you can save a pointer to the data itself so that you can always recreate the model if you need to. When people go through this process, they may end up with like hundreds of these experiments. And the idea is people will look at the parameters, look at the metrics, do some analysis on that, and figure out which one they want to deploy. When they select one, like for example this one, and they want to deploy it, MLflow also gives you the ability to use that model in different ways, in the different ways that we talked about, right? So I will switch over. Are you guys familiar with SageMaker here? Anybody? No, okay, so a few. Okay, so well, I'll use it anyway. So So SageMaker, from a very high level, is a service within AWS where you can essentially deploy models. And when you deploy a model, you end up with a REST API that you can use to exercise a model. So MLflow basically integrates with that. I'll show you how easy it is to deploy a model. So once you've developed a model and you have it in MLflow, the only thing you need is the run ID. The run ID, every experiment has a run ID basically. And then once you do that, you use this MLflow SageMaker module to deploy it. And this is all it takes, right? You basically call one function. You say, I want to deploy this model with this name, and then in this region on AWS, and that's it. This command takes about, I don't know, 5-10 minutes or so. But this work right here, before MLflow was around, you know, people would spend days basically doing the handover, right? From the model being developed and tuned by the data scientists to the DevOps people to deploy. This right here basically allows you to iterate very, very quickly on model development, model deployment, and all this stuff. There's a lot of value here. You know, if you take this out of your workflow, then of course you can focus on other, you know, more meaningful work, right, for your company. But essentially, this is how easy it is. At the end of that, once you deploy it, you essentially end up with a REST API where you can send JSON data, and essentially you get back a response, right? Like this one. This is the result of the score. So this is all very dependent on what the model is doing, but it's the same idea, right? No matter if your model takes one feature or 1,000, it's the same thing. And the idea, of course, is that MLflow essentially, you know, makes it really easy. And yeah, that's I think that's pretty much it. Let me see on this one. Yeah, that covers what I wanted to show today. Hopefully that gave you a good idea of what Databricks is and, you know, how we do machine learning on Databricks. So yeah, thanks, and I guess we'll take questions, right? Thank you. Yeah. So.
Okay, so now we're going to start the questions. We still have time to upvote the question on Slido. Feel free to go there and upvote your favorite question. So the first one is, in April, Databricks presented the koalas, the pandas for Spark, but since then, there were no new updates on the library. Any new updates coming?
Is the question about koalas?
Yeah.
Okay, yeah. Yeah, so Koalas is an open source project that we launched, again, about, I don't know, 5-6 months ago. And for those of you that are not familiar, Koalas is essentially a library where people that are very familiar with pandas, data frames, or pandas in general, can take all of that knowledge and bring it over to Spark. So if you were used to doing stuff in pandas in a single machine, now you can do the same API knowledge, bring it over to Spark, and do that in a distributed fashion. So that's what Koalas is. And the reason why that's important is because people do not need to learn the Spark data frame APIs, right? So as you can see, it would be beneficial for a set of users. So yes, we keep adding releases almost every month. Where the versions of the release version of Koalas is basically increasing. There's a lot of effort, a lot of work being put into Koalas, yeah, I mean that's I think that answers the question, right? So essentially, we keep iterating on the versions and on the releases. There's a lot of interest and there's a lot of focus being put on that project.
Okay, the second question is there any difference in performance when you use SQL interface instead of Python Scala APIs on Databricks?
Yeah, no, there is no difference. If you have a data frame and you interact with it and you do an operation on it, and you use Scala, Python, or SQL, it all goes through the same execution path. It all uses a Catalyst optimizer, which is a component within the framework that essentially tries to understand what you're doing logically, and then it translates it into a physical plan. And no matter what language you start with, it's all the same. It did not used to be like that in previous versions of Spark with the RDD APIs, but with the data frame APIs, that all changed, and it's all the same. The place where you may see a difference is if you have UDFs, which are user-defined functions. So user-defined functions allow you to obviously create a function that you define yourself to take a data frame with some column values and then come up with a new value, right? So that's that's one area where there is a difference. So if you create a UDF in Python, it will be slower than if you create it in Scala. And likewise, so that's the main difference.
What are the advantages of using Databricks system over configuring something similar with Kubernetes?
What is the benefit of using Databricks versus doing it yourself? Is that the question on Kubernetes?
Yeah, doing the same with Kubernetes, yeah.
Mm-hmm. Yeah, well, there's a lot of differences. I know this, again, firsthand. I come from Hortonworks, and they also have a distribution of Spark, right, within CDH and HTTP back then. There's a lot of differences. Creating and managing the clusters on your own, people do it, yeah. But it takes a lot of time. It takes a lot of work. There's a lot of edge cases that you have to deal with. I would say that doing 90% of that, is doable. But then the edge cases are where the real work begins. And, we have like 300 engineers or so working on this platform. So, replicating that is pretty difficult. People try, but one of the biggest benefits that we bring is a lot of things on top of what you typically get out of Spark, right? Like the whole idea of a unified workspace is very valuable for a company because basically you get it all out of the box. Things that we do with the clusters, when you create a cluster and you deploy it to a cloud, we have the idea of auto-terminating the cluster after X number of minutes of being idle. So we have a lot of things like that essentially, give you a lot of benefit. It saves you a lot of time. And not only that, but the optimizations that we have built that are not part of the open source Spark distribution, that's also a big time saver, basically, and money saver for companies. So, there's a lot of benefits. Yeah.
Okay, so the next question is, when we create a cluster, is it like a front end for Azure or AWS cluster systems?
When we create a cluster, is it what? I'm sorry?
Like a front end for Azure.
Oh, I see, yeah. Yeah, when a cluster is created, is it a front end for the Azure or AWS? Yeah, I guess I'll answer that question from the point of view that in Databricks, essentially what you use, the workspace UI, that is something that that lives on our AWS account. When you sign up as a customer, there's a setup process where from then on out, any cluster that you launch within Databricks actually is launched on your cloud account. So it's using your VMs, it's using your account, you're paying for all that. And so the UI is essentially, it's a proxy for you to interact with the cluster. Yes.
Okay, so what's the best way to parallelize custom pandas or NumPy functions?
What's the fastest way to parallelize?
Yeah, the best way or the fastest way to parallelize custom pandas or NumPy functions.
Okay, I think okay. The fastest way to parallelize between three things: pandas. What was the other one?
Custom functions, custom pandas or NumPy functions.
Okay, I'm not familiar with the second one. Do you understand that? No. Oh, okay. All right. So what's the fastest way to parallelize pandas or custom functions? I think that's a question. Okay, so I'll go with that. Well, so if it's pandas, I would say the best way is to either use koalas, if that's something that that can be done, and if not, to essentially use the data frame APIs that come with Spark. If it's custom Python code, your option is to essentially do a UDF that you can then call from within the data frame APIs.
Okay, so the next question is, how is security handled in a machine learning model deployed using ML flow?
Yeah. How is security handled for machine learning models deployed with MLflow? Okay. So typically, when you develop a model in Databricks, we have a lot of security built into the platform where you can essentially lock down a notebook and restrict access to that, right? To different people, different groups in your organization, however you wish. Basically, there's ACLs all around that you can apply. So that's on the development side. You restrict who can access the data, who can access the notebooks, and so on and so forth. Once you have a model in MLflow, the same ACLs apply there, where a given experiment can be accessible by a certain people that you define. And once you take a model and you want to deploy that to production, and you deploy it to something like SageMaker, for example, SageMaker itself has a lot of security ACLs built in. They use IAM roles, where you can essentially lock down who can and cannot access that model that is deployed.
Okay, so the next question is about how do we integrate Git or GitHub with Databricks?
Yeah, how do we integrate Git or GitHub? So out of the box, basically, there's two ways that people do it. One way is through the revision history tab here, where you can essentially take a notebook and essentially link it to Git. So you tell it, you give it the link, right, to GitHub, and then you give it the path and the branch and so on and so forth, right? So this is one way. After you do this, you basically have the ability to say, okay, save this revision of the notebook, and you give your note, and then it pushes it out to GitHub. So that's one way. The other way is, if you have many notebooks that you want to synchronize with Git, people write scripts to essentially use the CLI. We have a CLI, command line interface, right? That allows you to essentially reach out to Databricks and copy the workbooks to your local computer, and then you use the Git tools to essentially push it out. So those are the two ways.
Okay, what's the best language to work with Databricks and MLflow?
The best language to work with Databricks and MLflow? I would say that it depends on the user. Some people are very comfortable using Python. Some people are very comfortable using Scala. I think it all depends on where you're coming from. That's one thing that goes into that decision. And then the other one is the framework that you want to use. So for example, if you want to use, XGBoost, then Python may be a better option, right? There may be a Java implementation, and then you can possibly use Scala. So it all depends on what you're doing. Yeah, so, but I would say that most of the customers that I work with, when they're doing machine learning, 90% use Python.
Okay, since there's always the Bayesian person in every event, so is there any Bayesian optimization library implemented within Databricks?
Is there what kind of optimization?
Like Bayesian optimization.
Oh, Bayesian optimization?
Yeah.
Man, I don't know.
Okay. And how can I integrate Databricks with microservices?
How can you integrate Databricks with microservices? It all depends on what you're trying to do. I guess one very typical way is, by doing what I talked about a little bit, where you deploy a model to a Docker container, to SageMaker, to Azure ML. You end up with a REST API. And then all your microservices, when they need that service, they call that REST API. That's one way. The other way that I've seen it is if you have a microservice where an end user can come in and say, give me a report of the data from yesterday for these parameters, that component, that microservice, could use the REST API or the CLI to interact with Databricks, to send a job or create a job to run, and then, of course, get the results later. Now, these things typically happen asynchronously because it takes time to spin up the cluster, to run the job, and so on and so forth. So this is definitely not a synchronous thing that you do, but I've seen those use cases, right? So those are typically the two ways that components interact with Databricks.
Okay, so let's suppose I have a ML model which was done for Databricks. How easy is it to deploy it? How long that could take?
Yeah, so it's pretty easy. I think depending on where you want to deploy it, as I showed, it takes 7 minutes or so. Once you have a run ID for a model that you want to deploy, now of course you have to do some analysis, right? So if you have 1,000 experiments, you have to analyze all of those. You have to analyze the metrics, and you can either automate this or do it manually, however you need. In the end, you select a run ID, and then you use the ML flow libraries to either deploy it to SageMaker, or to a Docker container, or to Azure ML. So I would say it's quite easy to do.
Okay. What are the DBUs and how to optimize its usage?
What are DBUs?
Yeah.
And how to optimize it?
Yes.
Okay. So yeah, so that's a good question. So DBUs stands for Databricks Units, and just like many other cloud services, you pay per usage. So DBUs is the way we measure how much usage you've consumed. Like on AWS, depending on the type of machine that you use, you typically pay a rate. For the clusters, it's the same way. So if you have a cluster with like 10 machines, and every machine has 1 DBU charge per hour, let's say, of course, at the end of 1 hour, you're going to pay for 10 DBUs. If you have the same cluster definition, but with 20 machines, then of course you pay 20 DBUs. So we charge per DBU. And also, there's some variations in the way DBUs are counted, depending on what you're doing. But typically, there's 2 main categories. One is automated DBUs, what we call automated DBUs, and then the other one is interactive DBUs. So, yeah. So from a high level, that's our pricing model.
Are all Databricks features available on Azure Databricks?
Are all features available on Azure Databricks? Yes, I would say that, of course, our goal is always to have parity between the 2 platforms that we offer on AWS and Azure. There are minor differences. For example, on AWS, of course, typically people use S3. On Azure, they use ADLS, Gen 1, Gen 2, blob storage, and so on and so forth. So the goal is always to have feature parity between the 2. But of course, the underlying services may be different.
Okay, so one last question. Is there any integration planned with Kubeflow?
Is there integration plan with
Kubeflow?
Kubeflow.
Yeah.
Okay. Typically, our users don't, we manage the clusters for them. So the need for them to do anything with Kubernetes themselves with our platform is not there, right? Because as an end user, you know that when you want a cluster, you basically go to the UI, you create a cluster. Now we use Kubernetes under the hood, but that's all, that's all internal, basically. So typically our users don't have a need to do Kubernetes, with our stuff. Yeah.
Okay, so I know that there's a lot of questions here. The Databricks crew is going to stay with us in the happy hour, so you can just approach them and ask your questions. And now they're going to announce the raffle winner.
All right. Thank you.